So this is a real experiment. So you see the ground truth is red. The odometry is in blue, right? The green circles are the keyframe poses. So because it's keyframe, so it's supposed to be sparse. Because it's keyframe, so it's supposed to be sparse. Right? The circles are sparser than the continuous trajectory. So obviously the odometry, the P odometry is less accurate than the keyframe odometry. Sorry, keyframe positions, right? This is a experiment with loop closure. This is an experiment with loop closure. Red one is the ground truth, but this one has a loop closure, but the odometry is still less accurate. I mean, the odometry still has a lot of error. So you can try to calculate the ATE, the absolute trajectory error, using the keyframe position. The problem is the keyframe position is sparse. Right? So if you compare this method with this method, this guy, he sets a threshold of like 5 meters for the keyframe separation. You set 1 meter. So how are you going to compare the two trajectory with different sparsity?
Interpolate?
Yeah. So what I did is I used the blue odometry to interpolate the keyframe position. Right. So you can see the black line is interpolated by the keyframe position and the odometry. So that's to fix the issue of having to compare different trajectories with different sparsity. So remember the error for these experiments is the same as the this one is so can you see the number?
So, what is the context?
The other day I talked about that if you don't, the other day I said that if you don't evaluate properly, your trajectory with loop closure will be less accurate than the one without loop closure, right? So this is one real case scenario where you see if you just use odometry here is 1.7, 1.1. But if you use that keyframe, it's 0.6. But it's 0.6, but it's very sparse. So you have to like interpolate it to compare it properly. Okay. So just a groundwork of the benchmark. So we can start with the real